So we'll take a new file and save it with some name, let's say image process 1. Let's understand how to perceive an image. Okay, so by default Matlab has your current directory, right? Now you can read an image simply by passing the file name of the image. Let's say this is the file name, image.jpeg. Let me copy this file name. In Matlab you can read an image simply by imread command. The file name should be specified as a string and you can display the image by specifying that file name, right? imread for reading an image. By default it is going to take you to the current directory, and whatever image file name is there, that you can give in your program. Let's execute this. If you execute, you'll be able to see the image. It is being read and displayed by Matlab. If you change the file name, whichever image file name you specify, Matlab is going to read and display that image. So one of the ways of reading and displaying the images in Matlab is put the images in the current directory and then specify the file name. Okay, but in most of the cases it is very tedious to every time change the file name, right? This is much more easier approach, where if you could shown up with a file open dialog, and if you could possibly select an image from there, instead, without changing the code, you could visualize and read several images, right? So that is pretty simple in Matlab. What you need to do is, Matlab has a command called UI get file. In UI get file, you can specify which type of image you want the user to take, either JPG, PNG, or any type of images, and you can give a message to the user, enter an image, whatever way. Now this UI get file will open a file open dialog for the user. When user selects an image, it returns two values. One is the file name of the image that you have selected, and the second one is the directory. Okay, so you are a computer science student, you must know that in order to read any file name, we want to give the absolute path, that is C drive, users, desktop, so and so /imagename.jpg. So by combining the directory name and file name, you get the actual path of the image, right? So fname is equal to string cat path comma fname. This will create the entire file name. Okay, so fname is a variable that now stores an image which user has selected. So instead of passing any name, just pass fname variable. Just pass fname variable. Now when you execute this program, first time you can select this image. Okay, again if you run, as you see, it has opened a file open dialog. It has given a message, enter an image. If I select this one, it's going to show this image, and so and so. As a matter of fact, as a common practice, let us clear the workspace and close all the previous figure windows. If we do that, every time the image will appear like this, just like what we did in the case of plot command. You can use title. Okay. Now let us understand how Matlab handles the image. For that, you need to look inside your workspace. You can see that IM variable is 241 into 209 into 3 u int 8. Okay. What specifically it is any image will be having number of rows, number of columns, and one element in a row and column is known as a pixel. So if you take any image and if you keep on zooming the image such that, you see, if you keep on zooming this image, you'll be able to see this pixel. Okay. An image is combination of pixel distributed across the rows and columns. So how many rows and how many columns? 241 rows and 209 columns, and each of this pixel is in turn is having 3 bytes. U int 8 stands for unsigned integer of 8 type. Okay, into 3 means each pixel is represented by 3 bytes. So generally the images that we commonly deal with are known as color images or RGB image. Whatever color you see can be created by certain combination of red, green and blue. And let's understand what it specifically means. If you open MS Paint, now if you make something, okay, there is a tool called color picker. With color picker you can select this color and you can go for edit color. When you are editing the color, you see you have values like red, green and blue. As expected, red value is extremely high, about 237. Green is about 28, blue is about 36. Now what if I decrease the red a bit to about 180? It will be more on a different type of color. What if I increase the yellow a bit? So if you try to increase the yellow, this will be different color. So irrespective of whatever color you see in computers digitally, they can be reproduced by combination of red, green and blue, and their maximum value is 255. If I make this 0 and if I make this as 0, this is going to be the pure red. Similarly, if I make all of them as 0, this is a black color. All the colors being 0 is black color. If I make only green as 255, it is obviously a green color. On the other hand, if I make blue as 255, it is a blue color. On the other hand, if you make everything as 255, all the color means it's a white color. Okay, so all the images will be having pixels. Each pixel will have 3 bytes. 1 byte representing red, 1 byte representing green, 1 byte representing blue. So essentially Matlab considers an image to be a 3-dimensional matrix. Okay, first 2 dimension is for row and columns, and the third dimension will have 3 values, red, green and blue values. Okay, so which means that every pixel is made up of some green part, some red part and some blue part. Okay, let us now do some really interesting thing with Matlab. So what we understand is that our image IM is a 3-dimensional matrix with the first part as the red, second part as the green, third part as the blue. Okay, so let us play with the channel a little. See, if I make green and blue totally equal to 0, I'll get the red part of the image. Similarly, if I make red and blue 0, I'll get the green part of the image, and if I make red and green as 0, I'll get blue part of the image. So let us create 3 different images from this image IM. One is the red part of that image, one is the green part of the image, one is the blue part of the image. So let's say IMR is the red image is equal to IM. Initially I'm taking the actual image, then IMR of colon comma colon, all the rows, all the columns, comma 2 to 3 equal to 0. You know the meaning of this notation. I am keeping the first element, which is the red component, and making the green and blue component as 0. Okay. Similarly, let's take IMG is equal to IM, and IMG of colon comma colon for all the rows and all the columns, 1 in the steps up to 3 equal to 0. So first one will become 0, then it will add 2 with that, third channel will become 0. So red and blue become 0, it will have only the green part. Again, let us take one more image, IMB equal to IM, and IMB of colon comma 1 to 2 equal to 0, which means that red and green component has been made 0. So let's plot this in subplot. Instead of plotting an image over here directly, let's say subplot 2 comma 2 comma 1. Let's say subplot 2 comma 2 comma 2. IM show IMR. Subplot 2 comma 2 comma 3, IM show IMG green part, and subplot 2 comma 2 comma 4, IM show IMB blue part. Let's see now what happens. So let's take this image into consideration. If you take this image into consideration, this image has got a red part, this is constructing the red part, this image has got a green part, and this image has got a blue part. Now you'll be specifically able to see a very wonderful result if you select a leaf result, for instance. You see, green is much more prominent than the blue part. This image doesn't have any blue part, so you'll see that image being pretty darkish. Okay, so this is how we can actually extract the channels. Now if you have to consider this image, this image is nothing but actually combination of 3 images, right? One is a red image, one is a green image, one is a blue image. So what this image is, if you see IMR, IMG and IMB, all of them has got 3 columns. IMR is having 3 elements, but green and blue is 0. IMG is having 3 elements, but red and blue is 0, and so on and so on. Oh, what if I, instead of making them 0, I just select one channel? Okay, so here what I have done is, I have made the other 2 channels as 0, but the images still holds 3 channels. Okay, now let's, rather than making other channels 0, let's select the channels, which it means is IMR is equal to IM of colon comma 1. Okay, simply I am selecting the first part. IMG is equal to IM of colon comma 2, and IMB is equal to IM of colon comma 3. In earlier cases, I had selected all the columns, then had made the irrelevant 2 as 0. Okay, here I am selecting only the red part, only the green part, and only the blue part. So the images IMR, IMG and IMB will no more be 3-dimensional matrices. They will become 2-dimensional matrix. Why? Because I'm just selecting one dimension, only the red part, only the green part, and only the blue part. Now what happens when we print them? Subplot, because I'll be having only 3 images, 3, 1, 1, IM show. Let's give them a name, IM R1, IM G1, IM B1, so that we can compare. IM show IM R1. Red part. Let's take 3, 2, IM green one. This is green part, and 3 blue part. Let's now run. Let's select the same image and see the difference. Can you see the difference now? When you separate any of the channels individually from an image, that image will no more be holding the color information. For an image to be color image, it should have red, green and blue component. If you want only the color part, make the green and blue as 0. If you want the green part, make red and blue as 0. If you want the blue part, make red and green channel as 0. But it should contain all the 3 channels for the image to be treated as a color image. The moment you extract any of the channels, whether red channel, green channel or blue channel, that image is not treated as a color image. That is rather treated as a special image known as a grayscale image. Okay. So these images, all of these images are basically grayscale images. However, because red part is different from green part is different from blue part is different. When you separate the channel, you'll feel 3 different images. Now, in many of the papers that you study, you'll see something called we convert the images into grayscale image. Why is because there is a specific property with the matrix. In any n dimensional matrices, where n is greater than, in any m cross n cross k matrices, if k is greater than 2, if any matrix operation hold good for k is equal to 1, it will hold good for k is equal to 2, 3, 4, so and so. Meaning is, if you take any 2 by 2 matrix, say 2 into 2 into 8 matrix, that means you have a square 2 into 2 and you have 8 such matrices. If any matrix operation holds for the first, consider them as a card, okay, 8 cards one after the other in a pack, or let's say 2 into 2 into 52 matrix, let's say it's a pack of cards. So if any operation is supported by the first card, this is going to be supported by all the other cards, okay. So any image operation, if performed on the red channel, the same operation can be performed on the green channel and blue channel, and it is really simple operationally to perform any operation on one unit of the matrix rather than all the units, right. One matrix manipulation will be less time consuming in comparison to 52 matrix let's say 3 matrix manipulation. So many of the paper will tell you that you need to convert the image into grayscale. What we understand is, just by picking either the red channel, green channel or the blue channel, you can convert an image into grayscale image. And essentially, if you look into their data type, a grayscale image will not have into 3 parts. This will be row into column. Each pixel is represented by only the pixel values between 0 to 255. However, if you convert a grayscale from red channel, it will appear different. If you convert a grayscale from green channel, that will appear different. If you convert a grayscale from the blue channel, that will appear different. But image processing has got a formula by means of which you can combine the results from all the three channels and then you can get a final grayscale value. Or there is a Matlab command called RGB to gray. So instead of now 3, 3, 1, let's put 2, 2 so that we can incorporate the grayscale image also. Now let's convert the image into grayscale. IM gray is equal to IM is equal to RGB to gray IM. So RGB to gray is a Matlab command where if you pass an image, you'll automatically get a grayscale image. This RGB to gray implements a formula. If you press F1 on the top of that, you'll be able to see the this is the formula. Gray is equal to 0.299 into R. Gray is equal to 0.299 into R plus 0.587 into G plus 0.144 into B. Okay. So instead of that, let's first take RGB to gray and generate a grayscale image. Let us display the grayscale image so that we can understand what's going on over here. Subplot 2, 2, 4 IM show IM gray title gray using RGB to gray. So if you now execute and select any of the images, let us see. This is your grayscale image. If you just select red channel as your grayscale image, when you select only the green channel, when you select only the blue channel, and this is an image which combines these three, okay, and gives you the grayscale image. Now, because we have already separated the red channel, green channel and blue channel, we can also use, so let us understand how to use a formula in Matlab. Okay, so you can also put them in a formula. Using formula for gray conversion. Okay, using formula for gray conversion. What is our formula? See, that's why Matlab is so simple. This is the formula. Let's say, let's give it a name. IM gray 2. 299 into R. What is our R image? IM R1. Okay. Now, because IM R1 is unsigned integer 8, let's convert it into double data type. You see, IM R1 is unsigned integer 8. Okay. Similarly, green image is IM G1. Let's convert this into double data type. And B is IM B1. Let's convert it into double data type. Finally, when you convert everything into double data type, your result will also be in double. But you see, images are supported only for unsigned integer 8. So once your operation is performed, you can convert everything into unsigned integer 8. Okay, that's how simple in Matlab to implement a formula. You see, we saw a formula, we have use this formula, and we have got an image called IM gray 2. Okay. Now grayscale image using the formula. Okay. Now this is your grayscale image using the formula. This is the grayscale that Matlab has used. Do you see any difference? There is no difference because Matlab also uses the same formula. Okay. This is how the channels have been extracted. So this is basically how the color components of the matrices should be used. Now, whenever you see any image processing books, I mean whether it is AKGen or whether it is which is the other one, it's going out of my mind. Most of the chapters that you'll see will have examples which will be predominantly black and white images. Okay, so it is easier to perform any operation on one component, that is the grayscale image. In today's class we'll also learn how to apply certain transform and how to apply them on a color image. Okay, but before that, so what we learned is what is an image. An image is nothing but rows and columns of pixels where each pixel is a combination of red, green and blue component. You can separate the red, green and blue component from the image by creating an image and making the green and blue as 0 for a red channel, red and blue as 0 for a green image, and red and green as 0 for a blue image. But whenever you want to conceive the image as a color image, it has to have 3 channels. We also learned that if we select any of the channel from the image, the image essentially becomes a grayscale image. Whether you select a red channel, whether you select a green channel, whether you select a blue channel. Why it becomes a grayscale image is because it loses the color information. Once you select any particular channel, the image doesn't then have red, green and blue component. It does have only one value. Okay, so therefore it becomes a grayscale image. A grayscale image is one where, contrary to the color images, a pixel will be having only values between 0 to 255. They'll not be having 3 channels. They'll have only one channel, the values between 0 to 255. 255 is the highest number for 2 to the power 8. I mean, it is 2 to the power 8. So, and they don't have any signs, like there will not be any negative pixels, okay, negative values. So therefore, because a pixel in an image will be having values between 0 to 255, they are represented by an unsigned number. Okay, unsigned number where there is no sign, where negative is not possible. And because this is 8-bit, Matlab stores them in unsigned 8-bit format. Okay, now we'll do some image operations and then we'll go back and understand what this, I mean how these operations can be applied on the grayscale images, I mean color images, sorry. So essentially we have we'll read an image. Let's take another file name and save it as IP2. This is common for everybody's project because you have to read the file, right? IM show IM, and as a good practice, again this file also CLC clear all and close all. Let's directly convert this image into grayscale image. IM1 is equal to RGB2 gray IM so as per the literature, we'll first select an image, we'll convert it into as per the literature, we'll take a grayscale image. So IM1 becomes our image now. We'll perform certain image operation, we'll try to understand some of the image properties, and then we'll extend those properties and transform into the color image. Okay. If you, sorry, when you read literature about your respective projects or any papers on image processing, one of the very common terms that we'll get to hear or read is histogram. Okay, histogram equalization. We perform a pre-processing step as histogram equalization. So let's understand what is histogram equalization. See, number of colors present in a grayscale image is between 0 to 255. Okay. Now, in the image, few of the colors will be dominant. So one of the common terms that you get to hear is histogram. Now what is histogram? Histogram is literally a graph, a bar chart, or a count of number of times each pixel has appeared in the image. Number of times 0 has appeared, number of times 1 has appeared, number of times 2 has appeared, 3 has appeared, 4 has appeared, and so and so. Let's plot it. So subplot 2, 1, 2. You can plot a histogram simply by saying IM hist. So IM hist will not only calculate the histogram, it's also going to plot it for you. So let's take this. IM1 rather. I'm sorry. IM1 is our grayscale image. Okay. So lot of black areas and maximum part is whitish. Okay, few blackish, maximum part is whitish. Okay, now let's take a simple skin image. Okay, that's right. So let's take only this much as our image. And let's run this. Now I'll take a screenshot and put it over here so that we can later on compare. All right. Let's again run our code with normal. If you see this histogram and if you can compare it with your previous image, this is a skin sample where we have no cancer trace, okay, or no abnormalities, whereas This is a sample where we have the abnormalities. You can clearly see the difference between the histograms. Okay, therefore histogram thresholding is being considered to be one of the very common and very inexpensive in terms of processing ways of measuring whether there is any abnormality present in an image or not. Okay, we can perform the same step for literally any type of data. Let's try to see which type of data. So you could, if you wish, you could use this as one of your intermediate results. Okay, histogram analysis of the skin images. Okay, the left one is a skin with the abnormality, this is its histogram. Right one is the skin which is normal. Okay, and this is its histogram. Now let's take a normal leaf image. As cervical cancer doesn't have any visual textures, you cannot explain a cervical cancer with the visual changes. Okay, it has to be at the shape level, because there will be changes in the nucleus, there will be changes in the cytoplasm. So we'll come back to that later on. Okay, right. So normal leaf image. Okay, so using the histogram we can know which color is dominating in an image and so and so. So we were talking about understanding of the abnormalities in images depending upon the histogram. So let's just see the same thing for the case of leaves. Let's take an image, the leaf image, one which is having abnormality. If you see the histogram, obviously you can see a lot of black color part being present over here. So this is the case with your abnormal leaf. Now let's take a normal leaf and see what happens with the normal leaf. Let's take a normal leaf. If you observe the histogram, okay, the white part, it is almost like 3000. Okay, let us take the abnormal leaf to see what is the result. Their size is different, so it's a little difficult. We need to take leaves of the same size. Okay, in case the leaves are of different size, what we can do is we can resize the images. In this fashion. Okay, because your database images all may be of different sizes. While processing, you may not get the appropriate result. So in order to overcome this drawback, in many of the image processing applications, what we do is we just resize the images such that all the database images are of same size. And now the white pixels, this is about 4000, and the other pixel is about let's say 1000. Let's see the abnormal leaf, though both are of different plants altogether, but still. Okay, it's only about 1000. Okay, black part is quite high, the white part is only about 1000, but in the previous case it was like up to 3000. So we can based on this we can understand which of the images are normal or which of the images are not normal. In fact, if you process this image, both the images using color channel, this is a green image, This is a red image. This is pure normal leaf. Okay, you can see the red channel is almost like a black hole. Okay, why? Because there is no part of red present in a green image, so you can see almost like a black hole for a normal image. But if you take an abnormal image, because that will have a lot of part which is black, you'll not get exact black hole image. You'll see a lot of parts, specifically this parts where the abnormality is there, that will be very much prominent in the image. So by using different approaches, we can find out if there is any specific sort of abnormalities or not. The same thing is true for your brain image also. Now, when you observe the red component, will be having a very high intensity on certain places. If you observe that using, say for example, histogram, you'll have a different perspective. Now, one thing that needs to be known is that medical images, something like X-ray images and brain tumor images, whether they are color or not, they appear just like a grayscale image. Okay, more or less they'll be having the same information in all the channels. So if you process this image using our first method, you'll see that almost all the channels will be same. Whether you take a grayscale, all of them will appear same, because they have same data in red, green and blue component. So if you copy the same data in all the three components, that image, even though is a color image, automatically becomes a grayscale image, because red value is same as green value is same as blue value. Okay, the medical images are more or less what I intend to say is by default are grayscale images. Okay, so you cannot use color image processing techniques like red, green and blue, stuff like that in medical images. Histogram based histogram based segmentation of such images is also extremely difficult, because for a grayscale histogram will be almost spread out. Now there are many different types of thresholding. The other term that you hear very commonly in case of images is thresholding. Now in this particular case, if you take this data cursor, if you click over here, you see the index value is about 200. If you just click outside this, the index value is about 110. So the tumor is a very bright spot in the image. So one of the simplest way of detection of the abnormality is thresholding. How do we threshold? Let's say thresholding. Okay, so how do you perform thresholding? Let's say IM abnormal is equal to IM1 greater than let's say 150 in this specific case. Okay, thresholding is one where you are selecting all the pixels which are greater than 150. Those pixels will appear white, rest of the pixel will appear 0. Okay, figure IM show IMA. It's a very simple case. Okay, this is where the tumor area is there. Okay, this is where the original data is there. Now what you can do is you can do several things. You see, if you do a thresholding, the result, if you see IMA is a logical image. Logical image is another kind of image which contains only ones and zeros. 0 is black color, 1 is white color. Wherever your probable tumor is there, that portion is white, rest of the portion is black. Now let us try to apply the same thing on the leaf, or say skin cancer, skin area. See, as simple as that. Okay, rest of the all part is white, this part is black. Okay, now how you can incorporate this information back into the original image. See, this is a binary image. Okay, it is having only ones and zeros. If you open IMA, the result of thresholding will have only ones and zeros. Okay, generally what we do is we first convert such an image. IMA is equal to double of IMA. We convert this into double, and then we multiply 255 with it. Okay, so 1 becomes 255, 0 remains 0. So instead it becomes a grayscale image, even though it has got white and black, two colors, but it becomes a grayscale image. We convert it into and generally one of the channels we replace with IMA. If you do so and display, let's say this case, can you see wherever the abnormality is there, that is appearing with a different color altogether in corresponding to your original image. The same thing we can apply in this case. It's a generalized threshold. It has taken care of this entire image, so entire image is appearing like that. Let's go back and see the case of your brain tumor. Okay, so what we did was, after thresholding we got a binary image. This binary image we converted into grayscale image, and that information we changed. Okay, original image, one of the channels, you can change the green channel also, blue channel also, whatever, you can just replace that channel such that this area will be clearly marked over there. Okay, this is also known as region of interest selection. Okay, there is one very good thing. Instead of doing this, you can purely select only this much part from the image, making rest of the other things as 0. How you can do that? Don't multiply this with 255. Okay, just convert it into double. Double means it has got 0 and 1. Double means it has got 0 and 1. Now this is a matrix, right, of zeros and 1. You can scalar multiply this with any of the matrix. So you can scalar multiply this. For I is equal to 1, we have 3 channels now. IM of colon comma I is equal to IM of colon comma I dot star IMA. So any image processing operation which is true for grayscale images can simply be extended to color image using this simple loop. For I is equal to 1, 2, 3, that means separately for red channel, green channel and blue channel, perform this operation. See, if I had not written this, if I had given only 1, only red channel would have been covered. If I had given only 2, only the green channel would have been changed. If I had given 3, only the blue channel would have been covered. By putting it in a loop, the operation you are performing on a single channel can be extended to all the channels. So whatever grayscale image algorithms you see in different papers can be applied to any color image using this simple loop. Let us go back. one is unsigned integer 8, one is double, therefore it is showing that it cannot be okay. As you can see, rest of the other images has been deleted completely, eliminated, removed. There is nothing. Only that part where the abnormality is there, it has selected, it has kept that part. Apply it on the skin. Because the skin abnormality is almost inverse, you'll see a hole in between. Okay. If you do not want to get this hole, or if you want to eliminate the skin area, it's again simple. Either change the direction of the threshold, or just say IMA is equal to inverse of IMA. Okay. In Matlab, tilt operation is the inverse operation, which means ones will become 0, zeros will become 1. Then if you apply this algorithm, it is going to eliminate all the skin part and keep only the cancer part. Okay. So this is how simple it is to work with the areas. However, if you look at this image very closely, this image is quite large. Okay. That means even after selection of the cancer part, it has got a large area, okay, outside this. Now if you take any statistics of this image, say take the standard deviation or mean, a lot of part will be attributed by this black part, right, which is not really the image data. It is not really image data. So it is a common practice to take only a region of interest, that is only take this much part for the processing. Such kind of thing is known as region of interest extraction. For region of interest extraction, you have a method in Matlab called bounding box. You see, this is my actual area. Okay. Rather than multiplying this with the image, why not to get a rectangle around that and cut only that much part of the image. Okay. So in this case, you have got this entire image. But instead of that, in many of the applications where we take the image properties, this black part will attribute a lot of properties. Okay. So the larger the image is, larger the black part is, it will have that much a different property. So instead of that, what we do is, many a times we use one more method called bounding box method. Okay. How do we use bounding box method? Let's see. So let me save this as a separate file IP3. And after thresholding, I'm not going to multiply IMA with the original image, or I'm not going to make any changes in the original image. Rather, what I'm going to do is R is equal to region properties of IMA. Region properties is a command which will give several properties like area, bounding box, and so and so. Okay. I can just say R is equal to R of 1 dot bounding box. IM show, IM, hold on, rectangle, just plot a rectangle, position R. So R is a rectangle which will be having the coordinates of the starting and the end of this box. Okay. Instead of separating the image, we can just put the rectangle on the top of it. Let's see how it works. Okay. So what it does, it marks the precise area where the abnormality is there. Okay. Now, Let us try to perform the same thing over here. Are you able to see anything? Wait. See, it is putting a marker on and around the entire image. Why? Because this was also part of this entire area was part of this bounding box. Area 62,000 to 193. RR 108. 108, 5914, 133. uh, 139, it should have been selected. We have not used any specific method over here. This is a very general and very common ways of proceeding ahead with image processing. So what we know from this discussion is that the image will contain 3 channels. By analyzing the 3 channels and then by analyzing the histogram, we can understand the trends in the image. From there we can find out the normal, and from there we can find out the normal and abnormal. We can also implement a thresholding on the image. Okay, after implementing a thresholding on the image, we can get a binary image. That binary image is sometimes also known as the mask. Okay, in order to detect the abnormality, that binary image we can convert it into grayscale image by multiplying with 255, and that can be added or that can be appended with the original image in order to get a color version of the abnormality map. At the same time, we can find out a bounding box. Okay, we can find out a bounding box which is nothing but a rectangle across the region of interest, and we can put it onto the original image in order to get the actual data. So this is basically the pre-processing steps, simple segmentation that is valid in most of the projects in one form or the other, and we have shown how the same code can be changed a little bit in order to come up with most of the solutions.